Welcome to the next lecture as part of our Introduction to Chemical Reactor Design module, a part of the Catalyzed Transitions to Chemical Engineering course. In this lecture, we'll be covering Chapter 11 from the Fogler text, and the topic today will be non-isothermal reactor design and steady-state energy balances. Up until this point, we've mostly been considering how to design reactor processes when we can assume isothermal conditions, but sometimes that's just not the case. Many reactions are not going to be carried out isothermally, especially as our reactors maybe get larger and larger and our heat transfer equipment can't keep up. So the question then becomes, what happens when temperature varies, say, for example, along the length of a PFR, or when heat is removed from a CSTR? How do we model those scenarios? What we'll see is we'll use our same basic algorithm that we've learned throughout chapters 5 and 6, but we'll be adding an additional important step, that is including an energy balance that we must also solve simultaneously. So we'll begin by developing the energy balance and then showing how we apply it. To further appreciate why we might need an energy balance, let's consider the following first-order exothermic reaction that's taking place in an adiabatic PFR. So adiabatic meaning no heat transfer into or out of the system, and as an exothermic reaction, it will be giving off heat, thermal energy. And so, as we already know, as our contents of our reaction proceed down the length of our PFR, we'll be approaching higher and higher conversions, ideally towards a conversion of 1. Now, as our reaction proceeds, it will be giving off heat, and so if we're not removing that at a sufficient rate, our temperature will also be increasing as our reaction proceeds. And we know that our rate constants are a function of temperature. So as we go along the length of our PFR, our rate constant will be increasing, and that is the rate of our reaction will also be increasing. So we need to appreciate how the temperature changes as a function of conversion in our process. We can see that a bit more directly if we look at our design equations. So again, considering our mole balance, our rate law, and our stoichiometry, these are expressions that we're already familiar with. But let's also consider how our rate law varies as a function of temperature, specifically our rate constant, which we know we can model to capture the effects of temperature as such. And so if we are to combine then our expressions in a non-isothermal reaction, we can then see that our conversion, changes in conversion as a function of change in volume of our reactor are sensitive to the temperature. Again, we don't know yet how temperature in the reactor relates to X in a non-isothermal reaction. So we need to develop this relationship and solve for this as part of our design process. And we'll do this by developing and applying an energy balance on our PFR as well as other types of reactors. So we need to derive an equation that relates temperature to conversion. So we'll start with a basic energy balance, and then we'll convert that into something that's a bit easier to use and consider a few different scenarios. So if we begin by considering a closed system where we have no mass crossing the system's boundaries, this would be similar to, say, a batch reactor, we can write an energy balance that says dE, the change in total energy of the system, is equal to delta Q, the heat flow to the system, minus delta W, the work done by the system on the surroundings. Hopefully, these terms are familiar to you from the thermodynamics module. Now let's make things slightly more complicated and consider the scenario of an open system where we'll have mass flowing into and crossing the system boundaries. This mass can be flowing in and it can be flowing out. And as it does so, it can be adding energy to the system as well as removing it. So in this case, our expression becomes a little different. We still have the rate of heat flow into the system from the surroundings. We have the rate of work done by the system on the surroundings. But now we have additional terms for the rate of energy added to the system by mass flow into the system. That'd be the flow rate in times the energy in, total energy in of that stream, minus the rate of energy leaving the system by the mass flow out of the system. So the flow rate out times the total energy of that exiting stream. The difference in these terms we would equate with the rate of accumulation of energy within the system. And our streams typically are not going to contain just a single component, but they'll have multiple species. So in each of our streams, we need to consider the flow rate of individual species and the energy associated with those, both at the inlet as well as at the outlet. Now let's consider in a little bit more detail the work term of our energy balance. Work term, or W, again, is equal to the rate of work done by the system on the surroundings. And we can break it down a bit further and separate it into what's referred to as flow work as well as shaft work. Flow work being the work required to get the mass into and out of the system, i.e. associated with our inlet and outlet streams. And shaft work is equal to the work done by a stirrer or a turbine, say if this is a mixed tank system. So with that, we can further describe our work term as the flow work in and the flow work out, as well as the shaft work. Now we can plug these individual terms into our energy balance that we derived on the previous slide and further expand upon their contributions. In this case, we've collected the energy and flow work terms associated with each of our streams as further broken down by the individual species comprising those streams. Now let's consider more about the energy term, or the E sub I. The energy term is equal to the sum of the internal, kinetic, and potential energy, as well as any other energies associated with those streams. So here we can write a general expression that captures each of those potential contributions, but typically in chemical reactor design, or in chemical reactors in general, usually the kinetic, potential, and other energies are negligible, and what we're interested in is the internal energy, or U sub I. So we can simplify our larger expression to say that the energy is equal to the internal energy, and rewrite our balance as such, replacing E sub I for U sub I in our flow streams. Our internal energy term, U sub I, we can also rewrite in terms of enthalpy. If you recall from thermodynamics, the enthalpy is equal to the internal energy plus P sub VI, or V sub I. And then incorporating that into our energy balance, these terms then cancel. And we can rewrite that just with respect to the enthalpy of our flow streams for individual species coming in versus leaving our reactor. And rewriting that in one more way using the subscript 0 to describe the inlet and no subscript 0 to describe the outlet. So this now represents our a more usable form of our energy balance. And let's consider a case where we have steady state conditions. And then that simplifies by eliminating our accumulation term. In this case, then we will still need to figure out the individual contributions from all of the species entering and exiting our stream, our reactor in the inlet and outlet streams. And so if we consider a general reaction of A plus B goes to C plus D and their relevant stoichiometric coefficients, then we need to account for the enthalpic contributions from each of those potential constituents of our streams, as well as any inert that might be entering and exiting, say, for example, a carrier gas. So we can expand these summations to account for the flow rates of each species times the enthalpy of those species, both at the inlet and the outlet. Like we did in chapter 4, it's further helpful to write our flow rates in terms of conversion and to relate them to our limiting species, in which case we'll assume is the reactant A. So we can rewrite the flow rate of B in terms of the flow rate of A and conversion, and likewise for C and D. If we then combine these relationships and rearrange them as part of our steady state energy balance, then we can relate the difference of these enthalpic contributions between the inlet and outlet as such, where this term, additional term here, represents the heat of the reaction at temperature T. Putting that back together, okay, we can clean up the equations a little bit and represent them as such, which then can go into our steady state energy balance, which we can now write as follows, where we are now explicitly incorporating the heat of the reaction. Our energy balance is highly dependent on these enthalpic contributions from the individual species, as we can see directly from the equation. So how do we get these? Well, you may remember from thermodynamics that the way we determine the enthalpy at a given temperature is to consider the enthalpy of formation at a reference temperature, TR. That might be something like standard temperature and pressure, plus the energy it takes to heat up that species from that reference temperature to our actual operating temperature, accounting for the constant pressure heat capacities. So if we do that, then we can see that these enthalpy of formation at reference temperature T R cancel out. And so we can then write these differences in enthalpy for species I between the inlet and outlet as simply being equal to the heat capacity of I at the temperatures between the inlet and the outlet. Likewise, we need to be able to calculate the heat of reaction at our operating temperature T. And we can take a similar approach rather, if we know the heat of reaction at some reference temperature, we can then calculate that at our temperature of interest by accounting for the heat capacity of the species participating in that reaction and the difference in temperature between our reference temperature and our existing temperature or temperature of interest, and then incorporate that into our overall energy balance. So then returning to our overall energy balance with some of the substitutions that we've made, if we again assume steady state, we have no accumulation term. If we assume that all of our reactants enter at the same temperature, that is Ti sub 0 is equal to just T0, okay, as would commonly be the case if they're coming in the same feed stream, we can rewrite that as follows, where our heat of reaction is calculated by accounting for the stoichiometries and the heats of formation of our products and reactants. And we can calculate the delta Cp, or the overall heat capacity here, by similarly accounting for the heat capacities of our individual species and their stoichiometric contributions. So this would be our usable energy balance. We can begin from these equations whenever we're not sure where to start, and then start to make appropriate simplifications as well as substitutions, but depending on the reaction of interest and reactor design. Now let's consider the case where we'd have an adiabatic reactor. Again, this would be a scenario where there's no heat entering or exiting our system, so we're not cooling or heating the process. And let's further consider that our shaft work is 0. At least it's a very small contribution that we can assume it as such. So our Q and our W sub S, those go to 0. And this is a steady state energy balance. We can then rewrite this equation and solve for X conversion as a function of temperature. Remember, that's what we're trying to do. And we see then that there's a direct dependence on temperature if we're appreciating that this delta Cp T minus TR term is relatively small, meaning that we have a direct and almost linear correlation between conversion and temperature. Again, considering if these are adiabatic and exothermic conditions. We can flip things around and calculate how temperature changes as a function of conversion. This is actually what we set out to do, to understand how temperature changes as a function of conversion in, for example, a PFR, and then we can understand exactly how our temperature profile is changing along the length of our reactor as conversion is increasing. Okay, so returning to one of our first questions, why do we need energy balance? When we wrote our mole balance, we understand that our rate law changes, our rate constant changes as a function of temperature, which is going to affect our reaction rate. And we can plug that all in and combine that to come up with our design equation for our PFR, including as a function of temperature. But now, thanks to our energy balance, we furthermore have an expression that describes how temperature changes as a function of conversion, and we can plug that in here for T, so that we only have now conversion appearing over here on the right-hand side. So that's how we model an adiabatic PFR. What about CSTR, well, here we don't have any differential equations, and we just have an algebraic design equation. How we're going to model that depends on what information we're given. Okay, so let's keep in mind that in CSTR, it's well mixed, so there should be no temperature variation along the reactor. In fact, the temperature of our exit stream, much like the contents of our exit stream, are equal to the temperature and the contents inside the reactor. Again, CSTRs operate at the exit condition. So how we approach the adiabatic design problem for CSTRs depends on what information we know versus don't know. So for example, if we're given our feed flow rate and concentration, we know our Arrhenius constants, heat capacities, enthalpies, and we're given a target conversion. Then what we need to do is calculate the temperature of our reaction inside the reactor and the exit stream, and the volume required to achieve that conversion. So steps would be to solve the energy balance for T at the exit temperature, which we can do so since we know conversion. We'll then calculate K, our rate constant, at that temperature, and then plug that K into back into step B, into the rate law, so that we can then finally calculate the volume of our CSTR, i.e. in our mass balance design equation. Now, another scenario might be if we're given our flow rates, concentrations, Arrhenius constants, heat capacities, enthalpies, and the volume of the CSTR. We would then need to instead calculate both temperature and the conversion that we can achieve. So in this case, we just use the alternative form of our energy balance, where we're solving for X as a function of temperature now. We'll solve our CSTR design equations for X as a function of temperature. Okay, plugging in for our Arrhenius constants into our rate expression. We would then plot XEB, okay, the conversion determined from our energy balance equation versus temperature, and XMB, the conversion determined from our mass balance or design equations versus temperature on the same graph. And where the two intersect is the condition, temperature and conversion, that satisfy simultaneously both the energy and mole balance equations. So this intersection would be the solution. Of course, you don't necessarily have to do this graphically. You can do it numerically, but nevertheless, we're looking for the temperature and conversion condition where both relationships are satisfied. And finally, we'll conclude this module by talking about Chapter 16, Residence Time Distributions of Chemical Reactors. Now, so far in the course, we've assumed that all reactors that we're talking about are ideal. Okay, mostly that means with respect to their mixing environment. But most reactors in reality are not ideal. And again, like with the case of heat transfer, mixing becomes much more difficult as our reactors get larger. And we can see that the ability to achieve well-mixed conditions becomes more and more difficult to satisfy. So what we want to learn in this chapter is how do we quantify non-ideality using what's known as residence time distributions, or RTD analysis. So what does it mean to be ideal or non-ideal? Well, let's consider this from the perspective of residence time. Residence time, if you recall, is the amount of time that a molecule spends in a reactor. If we have an ideal reactor, then all of the molecules that enter the reactor spend the same amount of time in the reactor. So for example, if the space-time, if you remember that definition, okay, volume over flow rate, tau, if that's equal to 10 seconds, then the residence time of each and every molecule entering the reactor is exactly 10 seconds as well. That would be for an ideal reactor. The residence time distribution tells us that individual molecules will display a distribution of residence times. Okay, so in a non-ideal reactor, that means that we are accounting for the fact that some molecules may spend less than 10 seconds in the reactor. Some molecules may spend more than 10 seconds. Some may spend exactly 10 seconds. There will be a distribution, again, of residence time. But the important point is that not all molecules will spend exactly the same amount of time in the reactor. Why does this occur? Well, it depends on the type of reactor. It can arise due to disruptions in flow paths throughout a reactor, especially in a plug flow. It can arise due to non-ideal mixing in a stirred tank, where we can have some molecules bypassing or short-circuiting the tank, others spending more time in the reactor, others even spending a large amount of time in what would be referred to as dead zones, regions that are not well mixed. How do we determine the residence time distribution? Well, we do what are called tracer studies. We direct a tracer molecule. This is going to be an inert molecule that's not participating in any reaction. We inject that at the inlet of our reactor, and then we measure the concentration of that inert at the outlet over time. We can do this either as a pulse, okay, we sometimes would say a spike, or a step input, where we then have a step change in the inlet concentration that's sustained. In an ideal PFR, if we have a pulse or spike injection, then we would expect, if all molecules are spending the exact same amount of time in the reactor, then we should see then a spike also appearing at the outlet, more or less exactly representing what we introduced. On the other hand, if we have a non-ideal PFR and we introduce our spike, as that flows through the PFR, we'll have forward and backward mixing along the axis, okay, as a result of diffusion or other effects. And so what comes out, some molecules will come out ahead of our would-be spike, and some will come out behind the would-be spike, spending less or more time in the reactor, respectively. The concentration versus time plot that we get back from our RTD analysis, we refer to as the C curve. Using the results from the C curve, we can then calculate the E curve. Okay, this is our exit E for exit age distribution, also referred to as a probability distribution function. The E curve tells us the fraction of molecules that have residence times between 2 times. We calculate E of t by dividing the C of t over the area under the C of t curve. Qualitatively, the E of t curve will look identical to the C of t curve, but due to this normalization, the area under our E of t curve will always be equal to 1. And if we are to then integrate the E of t function, okay, between, say, T1 and T2, 2 times, that value will be equal to the fraction of material leaving the reactor that has resided in the reactor for a time between T1 and T2. Using the E of t curve or the E curve, we can then calculate the F curve or the cumulative RTD function. The F curve can tell us the fraction of molecules that have been in the reactor less than time t. So we determine the F curve by integrating our E of t with respect to dt from 0 to some time t of interest. So in this example, if we are interested in determining how many molecules were in the fraction of molecules that have been in our reactor less than 40, let's say, seconds in this case, okay, and that in this example, it would suggest that 80% of the molecules spend less than 40 minutes rather in the reactor. Since this is a cumulative function, it's always increasing, and it can take on a max value equal to 1, which, if you recall, was the total area under the E curve. Important for our analysis is also to calculate the mean residence time, T sub m, and the variance, sigma squared. The mean residence time is the average amount of time that a molecules spend in the reactor. If we have ideal and non-ideal reactors, the mean residence time should be equal to the space-time. So we calculate that by taking the following integral. We take the product of time and our E curve, ET function, by dt, and get the total area under that curve, and equate that to tau. Again, that's equal to the mean residence time. The variance tells us the spread of the distribution. We can use this to tell how ideal the reactor is by understanding how broad or not broad the spread of the distribution is. So we calculate that using the following function. So we take the product of t minus tm. So first we must calculate tm squared. That product times our e of t function times dt, and integrate the total area under that curve. So what should we expect for our ideal reactors? Let's consider the PFR and a pulse input. Okay. If we have a spike going in, we can represent a spike coming out using the Dirac delta function. Looks like this. And for an ideal PFR with a pulse input, we would expect the mean residence time, Tm, to be equal to tau. And since our curve would have zero spread, in the ideal case, our variance should be equal to 0. Okay. And we could calculate that numerically. If Tm is equal to tau, then our variance should be equal to 0 from the previous slide. For an ideal CSTR with a pulse input, in this case, we do not have a pulse output because we have mixing and back mixing with existing reactor contents. So the expected concentration, or C of T curve, that we'd expect for an ideal CSTR would look something like this qualitatively. So too would E of T. And we can model then our E of T function as e to the T over tau over tau. And so even in an ideal CSTR, some molecules will go through the reactor more quickly, whereas others will be going through more slowly, much different than the case of a plug flow reactor. So in this case, for an ideal CSTR going through the same equations of our E curve or F curve, we would expect that the mean residence time, Tm, should be equal to tau. In this case, though our variance is not equal to 0, our variance would be equal to tau squared. And so lastly, here's a few cartoons depicting some representative examples of what we might see for different RTD analyses. If we have a nearly ideal PFR, we should see a nearly perfect spike coming out with very minimal spread, minimal variance. Our ideal CSTR would more closely follow that C curve function of the that we saw for the ideal CSTR. If we have a PFR or PBR with channeling or dead zones, you see that we deviate very greatly from the nearly ideal case. with some molecules coming out more quickly, others taking a long time to exit the reactor. And CSTR with dead zones can have sort of similar behaviors, some molecules leaving quickly and others perhaps trapped in a dead zone, spending a very long time in the reactor.